When I teach quantum mechanics, I start with a simple promise. The math works. It predicts experiments with uncanny precision, but when I step back from the equations and try to tell a story about what the world is doing, the story gets strange. One of the strangest questions we can ask is this: can the future change the past? That sounds like a line from a science fiction movie. In the lab, it becomes a precise question about how to explain correlations between particles that are separated by large distances. Those correlations were first made famous by John Bell in the 60s. Bell showed that if you assume the world behaves like everyday sense of reality, like a cause always happens before an effect, like we have free will to independently choose measurement setting, and no spooky action at a distance, the latter is sometimes referred to as locality, then certain statistical patterns are impossible. Yet experiments show those patterns happen all the time. To explain those patterns, we have to give up something ordinary. Different choices lead to different pictures of reality. One of those choices is to allow influences that run backward in time. That is retrocausality. Tonight I want to take you through what that idea means, how experiments make the question vivid, and what it would mean for our sense of reality if the future could, in some sense, reach back and shape the past. Imagine two particles created together and sent far apart. Each particle is measured by an experimenter who can choose one of several measurement settings. When the results are compared, they show correlations stronger than any classical, locally causal story allows. Bell's theorem makes this precise. No theory that respects both locality and the independence of measurement choices can reproduce the observed statistics. The options that remain are uncomfortable in different ways. You can accept nonlocality, meaning something like an instantaneous influence across space, or you can give up the formal independence between measurement choices and the earlier preparation, a move that comes in two very different flavors. Superdeterminism explains the correlation by positing that measurement settings and the particle properties were already correlated, a view many find unpalatable because it seems to undermine the idea of free experimental choice and imply that everything is predetermined all the way back to Big Bang. Retrocausality, by contrast, keeps operational freedom. Experimenters still make free choices, but it allows those future choices to constrain the variables that describe the system of preparation. So the later setting and earlier preparation are statistically linked. Retrocausality is not the same as time travel in the cinematic sense. It does not promise paradoxes where you go back and stop your own birth. Instead, it proposes a different kind of causal bookkeeping. In retrocausal models, the state of a system between preparation and measurement can depend on both past preparation and future measurement settings. Think of it like a violin string fixed at both ends. The shape of the vibration in the middle is determined by the boundary conditions at the ends. If you change one end, the allowed standing waves change. In a retrocausal picture, the two ends of the preparation and the measurement, respectively. The pattern in between is shaped by both. This has an attractive feature: it can preserve locality in space. The puzzling correlations between widely separated particles arise because the hidden variables that govern each particle's dynamic evolution from the starting preparation stage are constrained by the future measurement already. These hidden variables are local along each particle's world line. So the correlations are explained without anything having to jump instantaneously across space. It also opens the door to formulations that respect the symmetry of space-time, avoiding the need to single out a preferred frame of reference. But do we have direct experimental proof for this type of strange behavior, that a future choice somehow changes the past? Some people say the proof is in the so-called delayed choice quantum experiments. In a delayed choice experiment, you set up a situation where a quantum particle could behave like a wave, which means it shows interference, or like a particle, which means it takes a definite path without showing an interference pattern, and you postpone the decision about which kind of measurement to perform until after the particle has already passed the critical region. The key idea to explain first is the so-called which path information. If there exists, even in principle, a record that tells you which route the particle took, for example, which slit, which arm of an interferometer, the interference pattern disappears and the particle behaves like a localized hit. If you erase that path information, which means removing any record that could distinguish the routes, the interference pattern can reappear. A common and vivid implementation uses entangled photon pairs. One photon, the signal, goes straight to a detector and is registered early. Its partner, the idler, travels to a separate apparatus where the experimenter can choose, sometimes long after the signal was detected, whether to measure a property that preserves which path information or to perform a measurement that erases it. Experiments showed that the interference shows up only when you pick out the subset of signal detections paired with those idlers that did not register the which path information. If you pick out the subset of signal photons paired with those idlers that did register the which path information, then there is no interference. So far, so good. Just ordinary quantum mechanical prediction. But here is the tricky part. The experiment can be designed so that the idler photons are recorded later than the signal photons are. In other words, when a signal photon was detected or measured, nobody knows if the which path information will be preserved or erased. This choice will be made later, when the idler photon was detected. That is why such experiments are called delayed choice. Then, the question is, how does the signal photon know it should behave like a particle or wave when it was detected? It can feel as if the later measurement of the idler photon retroactively determines what happened to the earlier event of measuring the signal photon. That feeling is powerful. It tempts a narrative where the future reaches back and writes the past. But we must be careful. The raw experimental facts are simply correlations. How we interpret them depends on the metaphysical framework we bring to the table. Delayed choice experiments are suggestive but not decisive. The same data can be read in multiple ways. A textbook collapse story can account for the statistics if you accept a non-local update of the wave function. A forward-time epistemic view treats the quantum state as information about possible outcomes and sees no need for backward influence. And of course, superdeterminism can also be made to fit, since it assumes everything everywhere can be correlated. The crucial point is this: experiments show correlations. They do not, by themselves, tell us the direction of causation. Retrocausality is one coherent way to read the correlations, but it is not the only one. To prefer retrocausality, we need additional reasons, such as conceptual simplicity in some respects, compatibility with relativity in others, or a willingness to accept time symmetry as fundamental. Let us imagine, for a moment, that retrocausality is a real feature of the world. What would that change in how we think about reality? First, it would shift the metaphysical status of time. We would no longer treat the past as a fixed, immutable block and the future as an open field of possibilities. Instead, the world would be more like a tapestry woven from constraints at multiple times. Events would be determined by a combination of past and future boundary conditions. The arrow of time might remain for thermodynamic and experiential reasons, but at the fundamental level, the laws would be time symmetric. Second, it would change our notion of causation. Cause and effect would not be strictly ordered along a single temporal axis. Causation would become a two-way street in certain quantum contexts. That does not mean we could send messages into the past or create grandfather paradoxes. The constraints that prevent signaling would still hold. But it would mean that the explanatory arrows we draw in our stories about the world would sometimes point both ways. Finally, it would change the metaphors we use. Instead of imagining the universe as a clockwork machine ticking forward, we might imagine it as a symphony where themes introduced at the beginning are answered later, and the harmony is determined by the whole score. The future would not be a blank page, but part of the composition. Physics has a history of changing our metaphors for reality. Newton gave us a clockwork universe. Maxwell and Einstein taught us fields in space-time. Quantum mechanics forced us to accept probabilities and entanglement. Retrocausality, if it survives scrutiny, would be another shift, less a return to mythic time travel, and more a subtle reweaving of cause and effect. For now, the future does not let us dial the past like a radio station, but the experiments whisper that the simple story of a one-way arrow of causation may not be the whole story. Whether we accept retrocausality, nonlocality, superdeterminism, or a refined collapse story, the lesson is the same. The The world is stranger and more beautiful than our everyday intuitions suggest. If you walk away with one image, let it be this. Imagine a river whose currents are shaped not only by the stones upstream, but also by the sea ahead. The flow we see is the result of both. Quantum mechanics invites us to learn how to read that river.